you get phenomenal voltage drops, like 10 to the 9 volts per centimetre. So the electric and magnetic forces are fantastic. You probably all know that Lorentz force about being proportional to the charge, brackets, field plus V cross B, close brackets. Those forces are enormous. And your metabolism would suffer because your metabolism operates by slight electrical polarization of molecules and atoms and weak forces. Go to one of these places and it will be totally zapped. So don't go visit a neutron star and don't take your credit cards. And all that seems to rotate like a solid body. We believe that the pulse period that we see or hear is actually the rotation rate, which is why I said in the first slide you're listening to a star that's spinning 11 times per second, because its pulse rate is 11 times per second. And they tend to spin fairly fast. The fastest is just over 1 millisecond, the slowest is a 10-second period. And you don't have to go out very far from a body rotating at that rate before you'll find you're travelling at the speed of light. So for a typical pulsar, you go out just 100 kilometres and you're travelling at the speed of light. So these things must be small. This is the kind of picture we have. In the centre is the pulsar or the neutron star spinning about an axis which is vertical in this diagram. You know that on Earth, magnetic north is not at true north. Similarly, on a pulsar, there's an offset, magnetic north is there, true north is around there. And it's the magnetic field lines, we believe, that form the beam of radio waves. So there's a beam of radio waves coming out the North Pole, North Magnetic Pole, and South Magnetic Pole. And as the star spins, this beam sweeps around the sky. And if it falls across the Earth, we see pulse, 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 at whatever rate the star is spinning. Of course, there'll be a number that we don't see, which I can illustrate with a laser. There'll be some whose beam goes around like this, whoops, and never shines on Earth, so we never see it. We probably see about 20% of them. And we know of about 2,000 these days. They are very weak emitters of radio waves. Most of the 2,000 that we do see are in the near half of our galaxy. There will be pulsars in the far half of the galaxy, but they're just that much fainter that we don't see them at all readily. And as for pulsars in other galaxies, well, they must be there, but they're very hard to see. Once you get this kind of mass spinning, 10 to the power 27 tons, it keeps spinning. Its moment of inertia is spectacular. And it's the devil's own job to make it change its speed. And so the pulses come around very, very, very accurately. The pulsars are gradually slowing. They're ultimately running out of energy, rotational energy. But the period derivatives are phenomenally small. These kinds of figures, a pulsar period will have grown by about 1 second since the age of the dinosaurs. They're really, really good clocks. And they're dotted throughout the galaxy, or at least the near half of the galaxy, so they enable us to do tests on relativity. And there have been a number of tests on Einstein's theory. I'm going to teach you just a little bit of general relativity without equations, but with hand waving to explain this slide. One of the things that Einstein predicted was that when you accelerate, you emit a new kind of radiation called gravitational radiation, sometimes known as ripples in space-time. And these ripples propagate out, and they carry away energy. So when you accelerate away from the traffic lights, be it on the bike, in a car, you're emitting gravitational radiation, just a little, and losing energy. As the Earth goes around the Sun, there's central acceleration, holding the Earth in a circular orbit. So where there's acceleration, there's gravitational radiation. Or where a pulsar goes around a companion star, that's quite common, there's gravitational radiation. It's strongest in the case of the pulsar going round another star, so I'll focus on that one. So, pulsar going round another star, gravitational wave emitted, energy carried away. When you've got a pair of stars and they lose energy, they move closer together, which means the acceleration is stronger, the speeds are faster, the orbit faster, there's more gravitational radiation goes away. So they lose more energy, so they move closer together. The acceleration is stronger, they go round faster, there's even more gravitational radiation, so they move closer together. The two stars will spiral in. The orbit will also precess. And this graph that I have up on the screen is the first detection of the first evidence of gravitational radiation from studying the orbit of a pulsar. It's been going for a number of years. It started in 1974. It actually goes on right up to the future. And this is to do with the angle of the periastron. And the data is shown by the dots. Those near the front can see that there are error bars, small ones there. They've gone by here. The error bars are, I don't know, a hundredth the size of the dot. And the line is not actually the best fit, technically. It's Einstein's prediction for what should have happened. And it fits beautifully. And that is the first and some of the best evidence that Einstein is right in his prediction about gravitational radiation. I'm going to skip those two slides. I've mentioned that these objects are very, very dense. Average density like the density of the nucleus. You get some very interesting condensed matter physics when you have those kinds of densities, and I'm going to spend just a few minutes talking about that. If you're not into condensed matter physics, and I know not everybody is, then just hang on to this idea. A neutron star is like a raw egg. It's got a shell on the outside, the only kind of star that seems to have a solid surface, a shell on the outside, and some funny gooey liquids inside. The slide that's up at the moment is marginally more sophisticated than that. It says the solid crust is about a mile or maybe a kilometre thick, and there's some funny heavy liquid inside. If you want the full works, go on the web and find this picture. But it's far too busy a picture to teach from. Sometimes you can have too much information in a slide. So I'm going to give you a simpler version of the structure of a neutron star. And I'm going to start us on the outside and work in towards the middle. We're talking about something that's 10 kilometers radius, so this is a 10-kilometer journey. But during that 10 kilometers, the density rises by 10 orders of magnitude. So there's a huge range of physics and ends up in the unknown. Note the number of question marks down at the bottom left. But we'll get there. We'll start on the outside with an iron crust, an iron polymer crust. You probably didn't know that iron could be polymers. It's because of the very strong magnetic field. The atoms are no longer spherical, they're cylindrical. And when you've got cylindrical atoms and large magnetic fields, you're into some physics devised by Larmor. And Larmor predicted the energy levels and the size of atoms in large magnetic fields. And they come in large size and small size. And you could start with a large Larmor radius, stack on top of it a small one, stack a large, stack a small, stack a large, stack a small, and make a polymer. A polymer is very non-spherical, and therefore very readily attracts other polymers to it. And you end up with a very, very solid lattice of iron 56. It has a density of about 10 to the power 9 kilograms per cubic meter, million tons per cubic meter, and a Young's modulus about 500,000 times that of steel. It's very strong. Going in a layer, we come to a region of neutron-rich nuclei. We still have a recognizable solid, it's body-centered cubic, but the nuclei that you find at each of the corners of the cell are getting rather special. A little bit of simple quantum mechanics. Have most of you met Schrodinger's equation in quantum mechanics? Okay. Particles in a potential well. And you probably know that because of Pauli's exclusion principle, you can put two particles with opposite spin in each energy level. And you stack them in, starting at the bottom, till you've got all your particles stacked in. Maybe there's one oddball left over, and then it's empty energy levels above that. Right, I know it's early in the morning, but scratch your heads. How do the levels of the energies depend on the size of the well, the width of the well? It's 1 over the width of the well. So as you go in a neutron star towards the center, the density gets greater, the space per nucleus gets smaller, the well gets narrower, so the energy levels go up. And this top energy level is beginning to get seriously high. Right, now suppose we have a radioactive nucleus that wants to do beta decay. You remember in beta decay, there's an electron and a neutrino that come out and share the energy between them. So you can't predict exactly what the energy of the beta particle, the electron, is, but you know its maximum. It's when it's got all the available energy. So suppose somewhere off to the left, there's a radioactive nucleus trying to do beta decay, and the electron's maximum energy comes here on this energy level diagram. Down here, all the energy levels are full. There's nowhere for that electron to go. There's no room in the end, no space for it. And it can't have enough energy to get in up here or higher where there is space. So the decay is prevented, blocked, not allowed. And so some neutrons that would really like to decay into protons and electrons cannot do so and remain as neutrons. And you get neutron-rich nuclei. If we go in a bit further still, the density's higher still, the width of the well is even narrower, the energy levels are even higher, and there'll come a point where the topmost electron has enough energy to bridge the mass gap between a neutron and a proton. And it allows what's called inverse beta decay. You can take a proton plus this energetic electron plus a neutrino and make a neutron. And so your nuclei become even more neutron-rich and even more radioactive but unable to decay. This is why these things are called neutron stars. They're rich in neutrons. So you get these nuclei that are getting fat on neutrons. And there comes a point where they've got so fat that they can't hold on to all their neutrons, and the neutrons start dripping out and roaming free. And we're now into the next layer, which I've described as a neutron superfluid. Have you done BCS theory, superconductivity, superfluidity? Anybody? No. Okay. The way you get superconductivity, superfluidity, is you have an electron over here with spin up, and another electron over here with spin down, and there's a force between them, so they effectively behave like a particle with zero spin. They're no longer Fermi-Dirac particles, they're Bose-Einstein particles. And Bose-Einstein particles like clustering in energy levels. You can pack as many as you want at the bottom energy level, and that's what leads to this superconductivity, superfluidity. You get a similar effect inside a neutron star, only this time we're dealing with two neutrons, opposite spins, act together like a particle with zero spin. You don't get superconductivity because we're dealing with neutral particles, but you do get superfluidity which means zero viscosity, no resistance to flow. So if the Pacific and the bits of sea near here were superfluid, you could go down to the shore, set a basin, plastic basin in the water, give it a little flick, and it would glide across to China. No resistance to flow. So, heaven help us, inside a rapidly rotating neutron star, we've got some superfluid, zero resistance to flow. What fun. Or what very difficult physics. And so on to the center, where there's a big question mark. Densities here are very, very high. So high that we don't really have much data on how material behaves. The way you get data for high densities is working at an accelerator, because when two particles collide together, they're temporarily very close packed, as if they were at high density. The snag is these things are neutron rich, and you don't normally accelerate neutrons. Like, you can't actually accelerate neutrons. You have to have charges to get accelerated. So, interesting. Density is about 10 to the 18 kilograms per meter cubed. We started at the surface around about 10 to the 9. So we've come a long journey. And because we don't have data on this kind of density for a long while, anything went. You got a favourite thing, you can have it in the centre of a neutron star. Bose-Einstein condensates, mesons, quarks, strange quarks, whatever you wish. Until very, very recently, when we started being able to pin this. A complicated slide. It shows how the material inside a neutron star might behave. There's a number of different models, and each of the lines is a different model. On the vertical axis, there's the mass of the star, and on the horizontal axis, there's the radius. And you can see some of the lines are green. They're the ones that contain really strange material, like quarks. Some of the lines are pink. They start over at the right and trail over here. They're the ones that contain nucleons, and some exotic stuff. Most of the lines are fairly sober equations of state, these things are called, and they're made just of nucleons, neutrons and protons, and things like that. And for a long time there was very little way of telling whether any of these were right or wrong. But recently we started to be able to get the masses of some neutron stars. And first of all we got this yellowy-orange one, which actually doesn't rule out any models. Then we got the orangey one, which begins to rule out one or two of the lines that don't get up to the orange. And then about 2 years ago, we found a neutron star with mass almost 2 solar masses, and there's another one just announced that also has a mass up here. So this red band is now probably about double the width it used to be, but there's 2 stars there. And you see that equation of state doesn't make it, nor does that, nor does that, nor does that, nor does that green one, nor does that green one, nor does that pink one. The only ones that make it through to give you neutron stars of this mass are the ones with nucleons only. So I think at last we're beginning to get a handle on some of these. To finish, I want to do something a little bit lighter. The name pulsar, or pulsating radio star, was invented by a journalist who interviewed us at the time of the discovery. And the name is now used for many, many other things. There's a make of car called a pulsar, at least in New Zealand. I found some geraniums called pulsars. And of course there are the pulsar watches. Quite a good name for a watch, given how accurate they are as timekeepers. But interestingly, in the US, the Pulsar Watch Company tried suing the radio astronomers for use of the name. They didn't know their history. And I have some records, like Guinness Book of Records for neutron stars, pulsars. The pressure at the center of one of these stars is large. think there's 24 zeros there. That's in compared